Okay, so mass percent, percent composition of a compound, and the use of that piece of information will be in calculating what is the actual formula of a compound. Now, things can get a little more complicated when we're talking about actual formula. So there's a couple definitions here I want to go over, and then we can kind of see how each relates to the data we can get from a calculation. We want to compare empirical formula to molecular formula. So the empirical formula is the ratio of the number of moles of each element in a compound. So the empirical formula would just be the simplest whole number ratio of the components. The molecular formula, which could also be thought of as the actual formula, is a whole number ratio of the empirical formula, right? So a compound could be a little more complicated in terms of its molecular formula than what we see in terms of its empirical formula. And just to give you an example here, the compound acetylene that's used in welding torches has the formula C2H2, 2 carbons and 2 hydrogens. But there's another molecule called benzene. It's used in things like paint thinners and similar applications, has the formula C6H6. Now, both of these molecules, say we wanted to determine the percent composition in terms of, say, carbon in these molecules. Well, for acetylene, C2H2, that would be the mass of 2 carbons, which is 24.02, over the mass of 2 carbons and 2 hydrogens. So we'd add 2.02, that would be 26.04. For the total mass, that would be 24.02 divided by 26.04, and that is 92.24% carbon in the sample. Well, think about those numbers, and what if we're looking at this compound instead, benzene, right? 6 carbons instead of 2, that would be 3 times what's on top of the fraction there. And 6 hydrogens instead of 2 would also be 3 times what's on the bottom, 26.04, right? So we know we could cancel out those 3's. That's the exact same ratio, 92.24% carbon. So the empirical formula really represents the simplest ratio of components because it represents the percent composition. So for either of these compounds, the empirical formula would just be 1 carbon and 1 hydrogen, because that would represent the same mass ratio here. 1 carbon would be 12.01, 1 carbon and 1 hydrogen would be 13.02. The empirical formula gives us that same percent composition. So empirical formula, just the ratio, but the molecular formula will actually correspond to what the molecule actually looks like. So what we'll see is there's some extra information we can use, which is the molar mass, right? We'll see that in the second example problem here. We can go from empirical formula to molecular formula if we have the molar mass, and we can do that because they have to be related by a whole number. This is the empirical formula. Multiply this by 2, we'd get the molecular formula for acetylene. If we multiplied it by 6, we'd get the molecular formula for benzene. So the 2 formulas have to be related to each other. Now, let's look at a couple ways we can kind of use percent, maybe not percents, but mass information, because the first one doesn't have percent, the second one does. Mass information to figure out what the formula of a compound is. So let's look at this first one. We combine 1.25 grams of germanium. So I'm just going to do a little reaction here to help keep track of data. And we're adding excess chlorine to it. Okay, so Cl. Now, you may remember from our description of naming, chlorine naturally occurs as Cl2, diatomic. That's more information than we need here. It'll be a little simpler if we just think of how much chlorine we're adding and not worry about the fact that real chlorine is Cl2. That would just complicate our equation. We're combining germanium to chlorine with chlorine, and we're getting this compound, GeXCl. And we don't know what X and Y are, so we don't know what the ratio of those is in the product. But we're told we start with 1.25 grams of germanium, we end up with 3.69 grams of the product, right? And we want to figure out what the formula is here. Now what's missing is the mass of chlorine that was used in the reaction, but right? To take right back to the beginning of chapter 3, mass has to be conserved, right? And as a result, atoms have to be conserved. The difference in these masses is how much chlorine was incorporated. So if we take 3.69 grams, we subtract how much of that is germanium, we're left with 2.44 grams. That is how much chlorine must have reacted in this particular reaction. Now from here, we have the two masses of the components. That's enough information for us to figure out what the ratio here is. So let me start with the germanium. If I have 1.25 grams of germanium, what I want to do is convert that to moles of germanium, because the formula, right, that we're looking for, the empirical formula, or the formula, describes how many atoms are present. That's going to be related to how many moles are present. It doesn't describe how many grams are present. So we need to take the mass information and convert that to moles. Now that I can find on the periodic table. So I find germanium, 1 mole of germanium. Here's germanium right here, 72.61 grams. So 1 mole of germanium, 72.61 grams. So that means in this reaction, we used up 0.0172 moles of germanium. Okay. Now I want to do the same thing with chlorine, because I know how much chlorine was used, 2.44 grams of chlorine. 1 mole of chlorine. How many grams is a mole of chlorine? I can find that in my periodic table as well. So I find Cl, it's 35.45 grams per mole. That will tell me how many moles of chlorine were in my sample. 2.44 divided by 35.45. Oops, typed it in wrong. 0.0688 moles of chlorine, right? So now we have the mole to mole ratio here. But what's important to recognize here is when we're talking about a formula like we are up here, those should be whole numbers or integers. So what we need to do here is convert these to integers. And this is maybe the more conceptually tricky step of this type of problem. So you want to be sure you kind of understand what's happening here. If I want to make these integers, right, it's not unreasonable to suspect maybe one of those in the formula is 1. So whichever value of moles is the smallest, I'm going to take that numerical value and I'm going to divide by it. So if I divide my quantity of germanium by 0.0172, that becomes 1 mole of germanium. And then if I divide the other one by that same number, that will maintain their ratio. So 0.0688 divided by 0.0172 gives me 4. So for every 1 mole of germanium, there are 4 moles of chlorine in this compound. So those are the values for X and Y. My actual formula here is 1 germanium and 4 chlorine. So we might recognize this as germanium 4 chloride if we were naming it. The charge on the germanium would be +4. Okay, now we've got another example here starting with percents. This problem is going to take a little more time, so I'm going to stop the video there. We'll pick up this one in the next video.